what are physicists looking for when they use terms like the theory of everything or a God equation?
Really, when physicists talk about a theory of everything, what we're really looking for is a theory that unifies quantum mechanics with gravity. So quantum mechanics being, one of the staples of modern physics. Einstein's theory of gravity being called general relativity, another one of the staples of modern physics, but there's sort of this incompatibility between them. And so what physicists are talking about with the theory of everything is a theory which reconciles this incompatibility, puts them together in a consistent way.
Okay, and to understand why they need to be reconciled, make sure we get the framework of what those two things are. So how would you explain quantum mechanics to the layperson?
So quantum mechanics is really a theory of very small objects, things like atoms, electrons. There's sort of this amazing fact about physics that physics at different length scales behaves differently. So the mathematical equations that you'd use to describe something like the construction of a bridge or a building, which are Newton's laws of motion, those are different than the physics that applies at very tiny objects like atoms, electrons, other subatomic particles. General relativity, on the other hand, as a theory of gravity, is really a theory about very heavy objects. So things like planets, galaxies, black holes. To describe the physics of these things really accurately, you need to use general relativity. And so really, when we're talking about trying to put together quantum gravity with, when we're talking about trying to put together gravity with quantum mechanics into a theory of what's sometimes called quantum gravity, we're really talking about a theory that describes objects that are both very small, like quantum mechanics, where quantum mechanics is relevant, but also objects that are very, very heavy or energetic. So objects that are small and energetic aren't quite described either by quantum mechanics or general relativity separately. You need to sort of put those together to describe objects like that, which is relevant for things like the singularity of a black hole, the Big Bang singularity. For these sorts of things, you need this theory of everything, the theory of quantum gravity. So first of all, the quantum realm, we have both theory and experiment for that. We have, there's this famous particle accelerator called the Large Hadron Collider, which smashes particles together, and we can describe that accurately using quantum mechanics. So there we have some experimental evidence. When it comes to quantum gravity, we really don't have the sort of technology to be able to achieve the high energies that are needed to really test quantum gravity or to probe quantum gravity experimentally. So when we talk about that, the issue here, I talk about this incompatibility. It's really a mathematical incompatibility that, you do these computations and they work incredibly well at, say, the Large Hadron Collider. But if you were to imagine building a particle accelerator that can get to much, much higher energies than even the Large Hadron Collider, that at some point, the mathematical equations would start predicting nonsense. They start predicting probabilities greater than 1, for instance. And so that's sort of when you know that this theory isn't giving the right answer. Somehow there needs to be a new theory which describes this. And you really put your finger on part of the reason why it's so hard to come up with this theory. Part of the reason is theoretically, the mathematical equations for quantum gravity are just incredibly intricate and complicated. The other part is that because there isn't really a direct way to probe it experimentally, this is an area where we're really having to rely on purely mathematical computations far more than in, the history of physics, where ideally you have sort of this back and forth between theory and experiment. And in this case, we really are just going almost exclusively on the theory.
So the high level of the problem is, like, Einstein would come up with a simple or complicated formula, E equals mc squared, but that can pretty much sum up relativity or how the universe works in a degree. You have something similar for quantum mechanics, but when you try to put these two concepts together, it just doesn't, the math doesn't work.
That's right. Yeah.
Okay. So you're working and others on a solution, and that's called string theory. How does that work?
Right. So string theory is really the only known mathematically consistent theory of quantum gravity. By quantum gravity, I mean a theory that combines quantum mechanics and gravity at very high energies. So that's really string theory's claim to fame. That's why it's important. That's why we study it, is that it's the only theory that we know of that really combines these two in a mathematically consistent way. The issue is with string theory, again, experimentally, not much evidence for it, not really any good way to test it. Also, just very complicated mathematics. And so we understand string theory well in certain sort of corners and in certain sort of approximations with certain simplifying assumptions. But to try to use string theory to actually derive, particle physics that we observe, to actually make the sort of predictions that we can actually verify experimentally, that's what's really hard. And that's what I work on, is trying. My research specifically focuses on trying to bridge the gap between string theory and experiment. But as I say, it's a very difficult task.
And how far out would you say we are from being able to, or is it ever going to be possible to do those kinds of experiments to prove a string theory?
Yeah, that's a really good question. I mean, I think, I think it kind of depends on what one means by proof. I think that it is reasonable that string theory could sort of give us, give us useful information that could lead us to favor certain theories over others. But I think what's hard to envision, at least at the moment, is the sort of really sharp prediction that's so clear and precise that, if we were to see this, then immediately we know that string theory is the right answer. String theory isn't, at least at the moment, in a place where it can make really sharp and precise predictions. And so, I think it's maybe useful, it may be increasingly useful for informing the way that we think about physics and informing, say, how we do experiments. But I can't imagine, at least anywhere in the near future, having something that's so concrete, such a concrete proof of string theory, that it would, win all the skeptics to the theory.
Yeah. So in string theory, when you actually get down to what it is, is it something to the effect of you get down to the atomic level and you have your little protons and whatever down there, but there's all this space in between? Isn't it kind of the reverberations of energy is the theory that's kind of holding everything together? Or exactly what is it? What are the...
Yeah, I'm not sure if I'm not sure if I would say it that way. I think the way I would say it, at least behind string theory, is that that all these objects that we used to think of as just being point particles, so like electrons and quarks and photons, in a particle physics treatment, those are considered to be just points in space, essentially. So they're zero-dimensional objects, right? They're just points in space. What string theory says is that those objects are actually strings. They're actually extended in one dimension. So they're one-dimensional objects. They have a length, so we call them strings, in contrast to particles. And the reason why this is important is that it turns out that when you, as I said, when you take two particles and you smash them together at really, really high energies, eventually you run into these problems. You run into these inconsistencies. Particle physics starts to make the wrong predictions if you treat them like particles. But if you treat them like strings sort of have these nice properties such that when you get to really high energies, things remain, the calculation remains well behaved. And so that's the reason why it's called string theory. And I guess that's the main thing, if you remember nothing else about string theory. Particles are actually strings, and it's a theory of quantum gravity.
Okay. I think you referenced it earlier, but if this issue's solved, if you can find some kind of correlation or something that pulls together quantum mechanics and I guess the cosmos or general relativity, what comes of that? How does that change the world in any way? What bigger answers what questions can that answer?
It's hard to see how this is going to have any sort of answers as far as like, is this going to lead to like better refrigeration? Is this going to help with like
answer questions like black hole questions or dark matter issues?
Yeah, exactly. But yeah, that's what I was going to say. But as far as like understanding the fundamental laws of nature and understanding black hole physics, understanding the Big Bang singularity, I think, understanding some of these fundamental questions about the nature of the universe. I think what's kind of unclear to me is, if we figure this out, will this revolutionize the way that we think about metaphysics? Will it revolutionize the way we think about theology? Possibly. I think it's tough to say right now because we don't.
How could it affect theology, do you think?
Okay, yeah. Well, I think
has it? I think it's affected your personal view on theology or faith matters.
Yeah, well, I think probably where it comes in most, where the connection between string theory and theology is, the connection that comes up the most often is in the context of the multiverse. So, string theory, part of the reason why it's hard to verify experimentally is that it doesn't seem to predict a single possible universe, just a single conceivable set of physical laws, but actually gives it rise to this entire landscape. Landscape is the technical term. This enormous landscape of possible universes, you could call them. Different sets of possible laws of physics of the universe could have followed. So, in our universe, there's this thing that measures how strong electromagnetism is called the fine structure constant. And it takes a value of like 1 over 137. And you can imagine there's some other universe out there somewhere in the string landscape that has a different value of that fine structure constant. And you can imagine that there's a universe that has, instead of the electromagnetic force and the weak force and the strong force, maybe it has 8 forces, or maybe it only has 1. So lots of different possible sets of physics. And for some people, I think this is relevant because when it comes to the question of fine tuning. So, the laws of physics just seem to happen to fall exactly in this life permitting range. And for a number of people, myself included, this is suggestive of some sort of larger design, that perhaps the laws of physics are the way they are because they need to be this way in order to give rise to intelligent, conscious life like us. So for some people, the multiverse, the possibility of a string theory multiverse could perhaps be a bit of a counter argument to this, because if there's zillions of universes out there, well, maybe some of them are going to have life, some of them aren't, but we just happen to find, as observers, we're necessarily going to find ourselves living in a universe that has life as opposed to one that doesn't. And so I think that string theory often comes up in these theological discussions of the multiverse. But I would also say, and I'm happy to answer more, but one thing I'll say is that I think our understanding of the multiverse within string theory is still in its very early stages. Nima Arkani Hamed, who was a faculty member at the Institute for Advanced Study, where I did my first postdoc, I remember hearing once saying in her talk that right now the multiverse isn't a theory, it's a cartoon. It's sort of this cartoonish picture of what might be going on. But it's one of those things that we still really don't have a great understanding of within string theory.
Referring again to the Marvel of the universe, that's another focus they're on, is multiverses. And but it's nothing like that, is it? Their version of multiverse is there's different versions of you living out very similar lives with the same friends and family with different outcomes.
Yeah.
You're not talking about duplicates of universes, right? Just various universes.
That's not, in this context, that's not what I'm talking about. I think some people would say that such things do actually exist. But right now, what I'm talking about is really the multiverse in the context of fine tuning. And so I'm really talking about not different copies of me in different universes, but rather different sets of physical laws across the different universes, right?
Yeah. One last question along these lines, anyway, up in the science realm, physics realm, is the realms, the multi-realms, or dimensions, excuse me. So does string theory, when the math is done, I believe it comes down to, is it 10 dimensions?
Yeah, right.
So does that mean the conclusion is there's 10 dimensions, we can only experience or see 4 or perceive, or does it mean there's more math to do to get us to a place of 4?
Sort of both, I think. I mean, yeah, it's the idea is that there are 10 dimensions, we only see 4, so the other 6 are somehow curled up in a really small fashion, so that we can't observe them, we can't observe their consequences, but they exist nonetheless. But it really within string theory, all of the interesting physics, I mentioned, you can imagine there's some universe in string theory that's like our universe, only the fine structure constant is different. There's another universe that's like our universe, but there's a different number of fundamental forces. The things that distinguish those different universes, in large part, boil down to the way that you curl up the other 6 dimensions into some sort of tiny little geometry. So that geometrically, the physics of our universe can be translated into geometric questions about what's called the compactification geometry, the 6 dimensions of space. So part of the issue, not this isn't the entire issue, but part of the issue is that the geometry, the mathematical, mathematically, it's just hard to understand all of the possibilities for how to curl up these 6 dimensions, because there's a lot of them. And so therefore, in order to understand how to get from 10-dimensional string theory to 4-dimensional us, we have this basic idea that we have these 6 other small dimensions, but in order to concretely make that jump between how do you go from 10-dimensional string theory to the exact laws of physics that we observe, you need to understand just more about the mathematics of this compactification. All
right. I'm going to ask you now I guess it'd be a theological question. We'll see if you can ponder this one. That I think is a great question for a physicist. I want to see what your answer would be. So Scripture talks about, Satan being the god of this world, and we wrestle not with flesh and blood, but principalities and powers. So basically, some kind of spiritual operation going on this planet, and it says they're in the heavenly realms. From a physicist's point of view, it's not talking about other planets. It says here, but then it calls it heavenly realms. Some kind of spiritual hierarchies going on. Does that spiritual concept from the New Testament make sense in the physics world? Is realm another word for dimension? Can they be possibly interchangeable? Or how do you see that?
Yeah. My own personal view is that I'm really hesitant to try to get out of physics a lot of these spiritual realities. I think that for, really, when we talk about physics, I think that physics really ultimately, its goal is to describe the natural world around us. That there's all of these, I'm sitting on this couch, there's this house, there's the water that I'm drinking, and all of these things are described by physics. I think that, science does an incredible job with describing these things. But what science itself doesn't do is tell us that there couldn't be some sort of other realities that aren't so amenable to scientific study, that can't be described in such a way. And I think that when we talk about these spiritual realities as Christians, that we shouldn't, necessarily try to fit those into the physical framework, but rather that we should understand that the physical framework doesn't need to encompass all knowledge that exists, that there could be other things out there beyond what we can observe. Or also, that perhaps perhaps sometimes there's a physical description of something, but there's sort of a deeper meaning to it. And so I think, I've heard this somewhere, and I like to say it a lot, that I think physics and science do a better job of telling us about mechanisms, and religion and faith do a better job of telling us about meaning. And I think it's best not to try to read meaning too much out of science, out of laws of physics or biology or anything else. And I think it's best not to try to work too hard to understand the mechanisms from a biblical perspective. I don't think that that's really what the Bible is trying to point us toward.
Physicists, or that I've seen anyway, just popular ones I would know of, like Einstein, Michio Kaku, they mention God a lot. Physics circles, they're not usually talking about the God of the Bible, are they? More of a pantheistic, that all of creation is what they're referring to as God. Is that right?
Yeah, I mean, I think a term that often gets used a lot is nature, with a capital N, and I think you do hear this a lot, even within physical, within the physicist circles at physics seminars. Physicists will talk about nature doing things one way or nature doing things another way, and they're kind of using this nature with a capital N like a little bit of a placeholder God. I'm not sure whether it's best to think of it as pantheistic or deistic, but I think really ultimately what the main difference is between that nature with capital N and the God capital G that I believe in is that I think nature with capital N just is completely indifferent to the affairs of humanity. That nature with the capital N is sort of divorced from humankind, and that we humans are just sort of this happy accident that happens to have come into existence.
When they use the word God, are they almost using it like Mother Nature?
I think so.
More of a term than a personage.
I think so. I mean, I should say, there are certainly, many religious scientists, many religious physicists out there, but I think you're right that for a lot of these people, that when when you read these books, when you hear them referring to God, I think that you're right. It's a little bit like Mother Nature.
So, you're in the same world, in the same study. How did you come to believe in, the God of the Bible and the Christian faith? How did that journey happen?
Yeah, so it's a long story, but essentially, I grew up in a very loving but also very non-religious family. I have a twin brother named Steve, and growing up for both of us, we just didn't think too much about religion. Never went to church, never read the Bible. Basically was focused pretty much just on school and sports. So those are the two things that I was really interested in. And we went off to college. My twin brother met a guy at his floor his freshman year. He was probably the first really serious thinking Christian that either of us had ever met. And so my brother and him started having conversations. Eventually, my brother decided he was a Christian, and he started talking with me about it. And I told him, look, Steve, I have trouble. Sorry, he tried to give me a copy of the Bible, some other books about Christianity to read. I told him, look, Steve, I have trouble finding time to read books that I want to read, much less time to read books that I don't want to read. That's just where I was with it. I always figured, I'm basically a good person. If there's a heaven, I'll probably go to it. But I was just more focused on academic excellence and having success as I defined it, as I saw it. And it was a lot of conversations, I guess, with my twin brother that really got me to start thinking about a lot of the bigger questions. And more than anything, maybe they got me to start realizing that despite referring to myself as a non-religious person, I did in fact have a worldview. I did in fact have, views on what is good and what is right and what is the afterlife. That I had come to have views about all of these things, even though I wouldn't have called it a religion. And so as I started talking more with him, I started having to, questioning a lot of my worldview, a lot of the assumptions that I brought to the table, things that I realized weren't necessarily based on certainly weren't based on science, but were more so just based on what I had internalized. And so as I started questioning, I started rethinking a lot of my positions. Ultimately, I had an experience where I just got to this point where I realized kind of that I wasn't such a good person, wasn't as good of a person as I thought I was. And kind of in that moment, a lot of what my brother had been teaching me, about forgiveness, about salvation, a lot of these things just seemed like buzzwords until I kind of realized that actually I needed these things. And the Christian story that my brother had been teaching me really started to make sense of my own experience. So yeah, ultimately, I guess it was kind of a long journey, followed by kind of this moment of significant transformation and coming to realize that I did in fact need forgiveness, and that Christianity just made sense.
How did it affect your view on your science studies, or did it? Did it give you a different outlook, or not a perspective? But did it bring it more? Did it make more sense to you even?
Yeah, I mean, I think one thing is that it really inspired me to want to go into science a lot more. I probably wouldn't have gone into science if I hadn't become a Christian in college. I think that really it was in large part thinking about a lot of these kind of deeper questions of meaning, of purpose, that got me interested. I also, something I came to realize is that for whatever reason, our culture seems to really care a lot about what scientists think about God. And so for me, I think I saw it as sort of an opportunity to be able to talk about my faith and to hopefully have an influence to help people grow spiritually, to help people kind of experience some of the happiness and the transformation that I experienced in coming to faith in the first place.
Great. That's why I have you on.
Yeah, exactly. Yeah. And now here we are. So
here we are talking about it. So your book's coming out in August. That's what got you on my radar. Just what's the quick summary of it? And can people, if I put a link, are they able to pre-order it?
I believe they are able to pre-order it. I know it's on some of the websites now. Yeah. So it's called Chasing Proof, Finding Faith. It's really my story. There's a little bit about my perspective on things as a Christian, as a scientist, and some of the arguments that I found convincing or didn't. But yeah, in large part, it's really just my story, the story of how I came to faith as a college student, and then my journey of faith since then. So it's been a little bit more than 13 years now that I've been a Christian, and in that time, I've had a lot of highs. I've also had a lot of lows, a lot of doubts, seasons of fear and anxiety, and so this book is kind of just talking about how I was able to go through all of those, and how my faith has changed, how my science has changed, how I've grown in all that time.
All right. I appreciate your time, Dr. Rudelius, and I'll put the book, the links, Amazon and wherever, I'll put it in the notes for you. All right.
Great. Thank you very much. Yeah. Thanks for having me.